So, hi. Hi! I am Melissa from Igalia, and welcome to the Rainbow Treasure Map, a talk about advanced color management on Linux with AMD Steam Deck. So first, if you are not used to the topic, you may find some useful links in this list. And when we talk about colors in the graphics chain, we should keep in mind that we have a wide variety of source content colorimetry, a variety of output display device, and also internal processing. And then users expect consistent color representation across all these devices. So to get it, the user space can use GPU accelerated color management. However, this requires an interface with the display kernel drivers that is currently missing from the DRM KMS framework. So since April, I have been bothering, the DRM community by sending email pet sets with more than 30 pets from the work of Joshua and me to add driver-specific color properties to the AMD display driver. Meanwhile, discussions on defining a generic color management interface are still ongoing in the community, and we are still not clear about the diversity of color capabilities among hardware vendors. To bridge this gap, we have defined a color pipeline for Gamescope that fits the latest versions of AMD hardware. It delivers advanced color management features for game mode mapping, ADR rendering, SDR on ADR, and ADR on SDR. So AMD frequently release new GPU and APU generations, and each generation comes with a new DCN version with display hardware improvements. For this work, we use AMD Steam Deck hardware and its kernel driver as a reference. The Steam Deck is an APU with DCN301 display driver. It's part of the DCN3 family. And knowing this is important because newer AMD DCN drivers inherit implementations from previous families. Additionally, each generation of AMD hardware may introduce new color capabilities. So it's important to familiarize yourself with your specific hardware. The AMD driver in the Linux kernel space consists of 3 layers. The first, top and down. The first, the DRM KMS framework, then the AMD Display Manager, the DM, and the AMD Display Core, DC. So we extended the color interface exposed to the user space by leveraging existing DRM resource and connecting them with the driver-specific functions for managed color properties. So to connect DC color capabilities and the DRM API, we needed to do a significant transformation of the color management functions and helpers in the AMD Display Manager. AMD Display Manager is the Linux-dependent part of the driver that connects the AMD DC interface to the DRM KMS framework. It's intermediates communication too. So, and the AMD DC is the OS agnostic layer. So examining its code that is shared between platforms, different platforms, and different DC versions help us understand the AMD color pipeline and hardware capabilities. Since the machinery for hardware settings and resource management are already implemented there, or most of that. So now we arrived, I started to talk about AMD DC, and so let's take a look at the AMD Display Core Next, the newest architecture for AMD display hardware. Here we have 2 blocks that have the capability to manage colors. The display pipe and plane, DPP, for pre-blending color adjustment, and the multiple pipe and plane combine for post-blending color transformations. So now let's see what we have pre-blending in the DRM API. This is what we have for color management before blending. Okay, it's, I can say nothing, but it's not completely true because we have color encoding and color range properties for the input color space conversion. But both input and output color space conversion are already linked to the generic, the current generic API, and it's not part of this driver-specific work. So in case you are not familiar with the AMD shared code, I am not an AMD expert either, but I talked about it in the last XDC. In short, we need to draw a map, link points, and navigate there. You can see that we have some post-blending color properties on DRM, but there is nothing before blending yet. But thanks to the shared code, much of the hardware programming for AMD was already implemented in the DC layer. You can see that below. So, and it's not only the properties that was missing, but also the connections to the DC interface. So that's when our search begins. Looking at the color capabilities of the hardware, we arrive to this, okay, here. Oh, where is it? Oh, sorry, not so good. Okay, we arrive at this set of color properties. I can say that it was not that like that because we built this pipeline and discovered our needs throughout each iteration. But okay, the first property was the plane D gamma. It was our first driver-specific properties before blending. It's used to linearize the color space from encoded values to light linear values. Here we can use a predefined transfer function and also user lookup table. I will call TF and LUT from now. So predefined transfer function are for this block is a hard-coded cube that go to the D gamma ROM block, and this is the list of the transfer function that the drive support for this block. So we also have one-dimensional LUT that has the usual size of 1D LUT in the DRM subsystem. That is the 4096. And it's an array of DRM color LUT elements that goes to a different block in the hardware, the DPP gamma correction block. Then, finally, we have our first path unlocked. And now we will introduce the next one, the color transformation matrix, CTM, for color space conversions. Yeah, the link. So it's a 3x5 fixed point matrix that goes to the DPP gamut remap. It's another block. And but here, we need to pay attention that there was a trap here because both post-blending and pre-blending were going to the same block, the pre-blending gamut remap. So we needed to work here to detach this CRTC CTM from there. I think, yeah, that from there to the right way. Yeah. So now each CTMs go to the right path. Yeah, and we have another path unlocked. Next, the ADR multiplier. It's a factor applied to the color values of an image to increase their overall brightness. Yeah, it's useful for converting images from standard dynamic range to a high dynamic range, ADR, and it can range beyond 0 and 1, so subsequent transforms need to use PQ transfer functions. Then we need a 3D LUT. But 3D LUT has a limited number of entries in each dimension, and we want to use it because of it, we want to use it in a color space that is optimized for human vision. That means in a nonlinear space. Therefore, user space need one 1D LUT before 3D LUT to linearize content before apply the 3D LUT, and then another one after that to linearize content for blending. Yeah. Oh, yeah. And then this first, the pre-3D LUT pre-3D LUT curve is the shaper curve. Here we enable two properties, one for predefined transfer function and another for one-dimensional LUT. But here there is no hard-coded curve. What we do is AMD has a color module that is capable to calculate the predefined curve from predefined coefficients. And this is the list of supported curves. So what it does, as we have TF and LUT values, the color module combines both and into one LUT that goes to the DPP shaper RAM block. And 3D LUT is our rockstar. 3D LUT is perfect for complex color transformations and adjustment between color channels. It's also more complex for manage and require more computational resource. So that's why the number of entries is limited. So an array and a 3D LUT contains samples from the approximated curve, and values between samples are estimated by tetrahedral interpolation in AMD. AMD support 17 and 9 as the size of a single dimension. And the blue is the outermost dimension and red innermost. Then we also need, as I told you, a post-3D LUT curve to linearize content, the color space before blending. This is done by the blend TF and LUT properties. It works similar to shaper LUT, that there are no harded curves for blending predefined transfer function. And the curves supported here are the same of the D gamma block that is calculated by the color module. The resulting LUT goes to the DPP blending gamma block. So we have our pre-blending properties connected. Okay, there was a conflict. If you see, there is a conflict between the DRM CRTC D gamma and the DRM plane D gamma, and it is inevitable. And our approach now is not accepting that both are set at the same time. We also optimized the color, the conversion of the frame buffer to wire encoding by adding support to predefined CRTC gamma, the gamma TF, the last one you can see. It operates similar to the shaper TF, no harded coded curve, and the TF and LUT values combined by the AMD color module, and the resulting LUT goes to the MPC gamma RAM block. So this is the AMD driver-specific color management pipeline on Linux, and armed with this comprehensive knowledge, you are now ready to enjoy the rainbow treasure of AMD display hardware. And yeah, conquer the world of graphics and visual computing. In this work, we have now the Gamescope Steam Deck embrace the color capabilities of the AMD GPU. And you can see in a high level, oh, the image is not so good, but yeah, it's just describing how we map the Gamescope color pipeline with each color block on AMD. And okay, my time is not okay, but okay. So DRM subsystem contain not only this treasure map, but many other hidden treasures from different vendors. And that means that the search for the rainbow treasure is not over. We want more complex transformation and adjustment available in Linux, and we want to expose all GPU capabilities from all hardware vendors to the Linux user space. Finally, I would like to thank Joshua and Harry for all the fun in this collaborative work. Also, I can say we made it together. And also Rodrigo Siqueira and other AMD display developers for the availability and all the feedback that they provided. Everyone in the DRI community who contributed to this adventure. And yeah, the amazing part of this, the power and impressive part of this work is not here, comes next with Joshua and the Rainbow Frogs. So yeah, is it. Thank you, and questions? Okay, sorry, questions? Someone want to ask something? Okay, you can ask Joshua. Next, not me, sorry. Nobody is raising hands, yeah. Hands. Okay, one more. There.
Is it working? Yeah, is it working? So the question is the following. If I remember correctly, this uses the proprietary properties. I mean, this work, isn't it?
You mean how to use it?
No, I mean that your work uses driver-specific properties, not the generic.
Yeah.
Yeah, okay. Do you plan to make them available to other drivers? In some way, I saw the concurrent proposal. What is the plan for the convergence between?
Oh, I see.
Yes.
Yeah, this is like our short-term proposal to have something to start to understand what we have available in the system, in the subsystem. But our long-term plan is to adopt this in a generic API, in the generic interface. It will be easier for AMD because we already mapped everything. It's just a matter of switch to a different interface. But the programming setup and resource management are done. So, but our long-term plan is to adhere the generic interface. Yeah.
Which user mode did you validate this with?
I didn't get.
Which user mode did you validate this pipeline with?
Which user mode?
Yes.
You mean user mode driver?
Yes.
But in the KMS, we use a generic interface. It's not by user mode driver. I mean, it's not like Mesa. Is that thing?
Do you mean which composer?
Yes. Yeah. I meant which composer?
Oh, the Gamescope.
Okay, so the Gamescope
Compositor,
is plugged in with AMD specific properties, and that's how you validate.
Yeah, Gamescope use the driver specific properties right now.
Thank you.
It's the next presentation. We'll clarify you about how it works.
We have a question from the Matrix. What is the situation with upstreaming the vendor-specific properties? We usually don't allow driver-specific
Yeah.
properties nowadays.
Yeah, it's still in place, I can say like that, but what we are doing is to use a guard for these properties, at least for who is interested in, experiment and start to be more familiar with the properties can already play with that. And we are in the fourth version. I think it's maybe the last one, and it will be in the upstream sooner, I think so. Because the generic API, as I said, is discussion is still ongoing. So we will need more time to define it. Yeah. Time is over. Thank you. Bye.